Tonight, we embark on a journey, a quiet, contemplative drift across the vast, silent ocean of space to a world nestled 124 light years away from our own familiar blue sphere. This distant realm, a planet orbiting a dim red star within the majestic, ancient constellation of Leo, whispers secrets that could, quite profoundly, alter the very bedrock of our understanding, of our deepest assumptions about whether we, here, are truly alone in the cosmic tapestry. Scientists, using the extraordinary, golden eye of the James Webb Space Telescope, have peered into the delicate veil of this faraway world's atmosphere. And within its swirling gases, they have discerned the unmistakable chemical fingerprints of molecules that, here on Earth, are crafted exclusively by the intricate machinery of living things. This detection carries with it an almost breathtaking confidence level, resting at 99.7%. This leaves us with a mere 3 in 1,000 chance, a whisper of a possibility, that this could simply be random noise, a fleeting statistical anomaly in the grand cosmic data stream. This enigmatic planet, this captivating sphere, has been tentatively, yet evocatively, christened an ocean world. And its atmosphere, in a manner of speaking, resonates with the distinct molecular cries, the very essence of compounds that are vigorously exhaled by the marine algae that teem within our own Earth's boundless oceans. It is a symphony of sulfur, a profound chemical echo across the interstellar void. Prepare yourselves, for the narrative that unfolds next will gently, yet firmly, challenge every assumption, every preconceived notion you might hold dear about the prevalence, the very nature, of life throughout the universe. So, before you get comfortable, take a moment to like the video and subscribe. Let me know in the comments where you are in the world and what time it is for you. Imagine, if you will, this delicate celestial ballet. Picture a colossal, dark silhouette, the body of a planet, slowly, majestically, beginning its transit across the luminous face of its parent star. For a precious few hours, a minuscule, almost immeasurable fraction of that fierce starlight, which has traveled untold distances across the cosmic void, finds itself momentarily interrupted. It does not merely pass by, but rather, it is compelled to filter, to sift, to gently caress the gossamer, thin atmospheric layers of that distant, alien world, before it continues its epic journey across the light years, finally, gracefully, reaching our waiting telescopes here. And within that sifted, ethereal light, carried across the boundless dark, lie profound secrets. The James Webb Space Telescope, with its unparalleled precision and sensitivity, captures this precious, filtered starlight. It then performs an astonishing feat, splitting this unified beam into a breathtaking, intricate rainbow of colors, a spectrum far beyond what our human eyes can perceive. Each individual chemical constituent, each unique molecular species suspended within that distant, alien atmosphere, possesses its own distinct appetite for light. It absorbs, with exquisite specificity, certain wavelengths, certain hues from that celestial rainbow. Methane, for instance, greedily consumes specific reds within the infrared spectrum. Carbon dioxide, in its own characteristic dance, swallows particular infrared wavelengths. And water vapor, that fundamental ingredient of life as we know it, imprints its own unique, undeniable signature upon the passing starlight. Scientists refer to this elegant and immensely powerful technique as transmission spectroscopy. It operates much like reading a barcode, intricately etched, not onto a product, but directly into the very fabric of starlight itself. Each dark line, each subtle dip or peak in the spectral barcode, corresponds to a specific molecule, revealing its presence, its abundance, its very identity. This is not some speculative, untested theory. This technique is confirmed science, a well-established and rigorously validated method that has been successfully employed to characterize the atmospheres of dozens upon dozens of exoplanets, those distant worlds beyond our solar system. When this particular ocean world gracefully transits, or passes in front of its parent star, the James Webb Space Telescope meticulously detects a subtle, momentary dip in the star's overall brightness. This drop in luminosity is, in itself, a testament to the planet's presence. But far more importantly, and far more exquisitely, the telescope captures those infinitesimally subtle, yet profoundly meaningful, fingerprints left behind by every single molecule, every single atom, every single chemical compound, suspended and drifting within that alien sky. The entire process is one of breathtaking precision, a marvel of human ingenuity and cosmic observation. The telescope itself, this golden sentinel, does not reside on Earth. It floats serenely, majestically, a million miles away from our bustling planet, far beyond the turbulent, interfering layers of our own atmosphere. From this pristine vantage point, nothing terrestrial, no atmospheric haze, no human-made light pollution, no terrestrial interference, can possibly obscure or distort its crystal, clear view into the profound depths of the cosmos. Its colossal mirrors, those magnificent, segmented gold-coated panels, are specifically designed and meticulously crafted to capture infrared light. This is the very wavelength range, the precise portion of the electromagnetic spectrum, where these crucial, telltale molecular signatures, these whispers from distant atmospheres, truly shine brightest, revealing their secrets with unparalleled clarity. But here, dear listener, is what elevates this discovery, what truly makes it so profoundly revolutionary. The James Webb Space Telescope possesses an astonishing capability. It can detect chemicals at concentrations as incredibly low as parts per million. To truly grasp the magnitude of this sensitivity, consider this analogy on Earth. Detecting a chemical at parts per million would be akin to finding a single, solitary drop of ink, perfectly dispersed and identifiable, within an entire, Olympic-sized swimming pool. It is a testament to the telescope's engineering, a whisper of detection in a vast cosmic ocean. The invaluable data, the raw information gleaned from these meticulous observations, arrives in the form of intricate graphs. These graphs display a series of subtle yet distinct dips and peaks at very specific wavelengths along the infrared spectrum. Each individual dip, each gentle valley in this cosmic waveform, represents a particular molecule absorbing light, greedily taking a portion for itself. The task then becomes one of meticulous pattern matching. Scientists carefully compare these observed patterns against extensive, precisely measured laboratory spectra of known chemicals. Match the pattern, and you identify the chemical. For instance, methane, that relatively simple yet profoundly important organic molecule, exhibits 4 distinct, characteristic absorption bands within the infrared. Carbon dioxide, another crucial atmospheric component, reveals 2 strong, unambiguous features. And water, the very elixir of life, leaves behind 3 unmistakable, unique marks. It is a molecular signature, written in light, for us to decipher. The James Webb Space Telescope employs 2 primary, highly sophisticated instruments for this intricate work of atmospheric detective work. One is affectionately known as the near-infrared spectrograph, or NAR-SPEC. This instrument meticulously examines wavelengths spanning from approximately 0.6 to 5.3 microns, a crucial band for detecting many organic molecules and water vapor. The other, equally vital, is the mid-infrared instrument, or MIRA. MIRA delves into the longer, cooler infrared wavelength, scrutinizing the spectrum from 5 to 28 microns. Together, these 2 powerful instruments collaborate, synergistically combining their capabilities to construct an incredibly complete and detailed picture of precisely what chemical compounds, what molecular entities, are gracefully drifting and swirling within these distant, alien atmospheres. When these dedicated scientists meticulously aimed the Webb telescope's golden gaze at this fascinating ocean world, they anticipated, based on previous, less precise observations, that they would detect the familiar signatures of methane and carbon dioxide. Both of these gases had, in fact, been tentatively detected before, utilizing the older, yet still remarkable, Hubble Space Telescope. However, the older instruments, while pioneering, inherently struggled with the kind of exquisite precision and detail that Webb now offers. What the scientists ultimately discovered, however, was something entirely different, something utterly unexpected. It was a revelation so profound, so startling, that it compelled them to meticulously, painstakingly, check and recheck their instruments not once, not twice, but 3 separate times, just to ensure that their findings were not some error, some elusive glitch in the intricate machinery of observation. The graphs, those silent tellers of cosmic tales, displayed a series of undeniable absorption features, distinct valleys in the spectrum, that matched only one thing, only one specific class of molecules, dimethyl sulfide, or possibly its very close chemical cousin, dimethyl disulfide. Both of these molecules share remarkably similar spectral signatures within the specific wavelength range that Webb had observed. The signal, strong and clear, manifested itself at wavelengths precisely between 4 and 5.2 microns. Multiple distinct absorption bands, those characteristic dips in the light spectrum, lined up with astonishing perfection with meticulously obtained laboratory measurements of these specific sulfur compounds. Furthermore, the sheer strength, the undeniable depth, of the signal indicated atmospheric concentrations that significantly exceeded 10 parts per million. To truly appreciate the scale of this finding, consider this Earth's atmosphere, our own breathable air, contains these very same molecules, these subtle whispers of life, at concentrations of less than 1 part per billion. This means that some profound and powerful process, is actively producing these molecules on this distant world at rates thousands of times higher than anything we observe here, in our own vibrant biosphere. But, dear listener, what follows next is even stranger, even more tantalizing, and perhaps even more compelling. The scientists, in their meticulous pursuit of truth, ran the observations not just once, but twice, utilizing different instruments on board the James Webb Space Telescope. And both times, with unwavering consistency, the exact same signature appeared. The statistical probability, the sheer improbability, that this remarkable signal could have occurred by sheer random chance, by some cosmic fluke, sits at an infinitesimally small 0.3%. In the precise and rigorous language of statistics, this is referred to as 3 sigma certainty. It is a level of confidence that far transcends mere coincidence, a statistical whisper that demands our profound attention. While it is not yet quite enough to declare an unequivocal, definitive victory, to plant the flag of certainty, it is undeniably far beyond the realm of simple chance. To truly reach the scientific gold standard, that almost mythical 5 sigma certainty, the level at which a discovery is considered irrefutable, scientists would require just 2 or 3 more observation windows. These crucial additional observations, these further glimpses into the alien sky, could potentially happen within the next year. The wait, though agonizing, promises to be profoundly significant. The next question, then, becomes not just obvious, but absolutely paramount, a resounding echo in the silent halls of scientific inquiry. What in the vast, intricate tapestry of cosmic chemistry could possibly create these specific molecules, these profound sulfurous whispers, in such staggering, almost incomprehensible amounts? On our own vibrant planet, dimethyl sulfide, this intriguing molecule, has only one unequivocally confirmed source: life itself. More specifically, it is produced by the countless trillions of tiny, microscopic organisms that float, drift, and thrive in our planet's sunlit oceans, organisms collectively known as phytoplankton. These microscopic algae, these invisible architects of our atmosphere, produce a compound called dimethylsulfoniopropanate, or DMSP, as an integral part of their metabolic processes as they grow, photosynthesize, and multiply. When these phytoplankton inevitably die, completing their life cycle, or when they are broken down and consumed by the tireless work of marine bacteria, this compound undergoes a remarkable transformation, breaking down into the very molecule we are discussing, dimethyl sulfide. This gas, this telltale signature, then escapes from the ocean's surface and drifts into the atmosphere. You can, in fact, quite distinctly smell it. If you were to walk along any vibrant, salty beach, that sharp, slightly pungent, yet strangely invigorating scent in the air, that unique olfactory signature, is, to a significant degree, the presence of dimethyl sulfide, a breath of the ocean's life. For decades, dedicated scientists have meticulously scoured the realms of chemistry, tirelessly searching for any plausible, non-biological pathway, any abiotic mechanism that could produce this specific molecule in planetary atmospheres at meaningful, detectable scales. And with every experiment, every theoretical model, they have, to date, found absolutely nothing that works, nothing that can replicate the biological efficiency and sheer volume of production. Laboratory experiments, under carefully controlled and highly specific conditions, can, indeed, create trace amounts of dimethyl sulfide. This can occur through intricate reactions between methane and hydrogen sulfide, often requiring very precise ratios of ingredients and specific energy inputs. However, these abiotic pathways are demonstrably inefficient. They necessitate exact and delicate balances of precursor molecules and energy, and crucially, they produce dimethyl sulfide at concentrations that are orders of magnitude, thousands of times, lower than what we observe even in Earth's atmosphere, let alone the astonishing concentrations that the James Webb Space Telescope detected on this distant, enigmatic ocean world. Here, dear listener, is precisely why this particular finding, this chemical whisper from afar, carries such profound weight, why it truly matters in the grand scheme of our cosmic search. Most other potential biosignature gases, molecules that could, in theory, indicate the presence of life, suffer from a fundamental ambiguity. Methane, for instance, a common gas, can certainly arise from biological processes, but it can also be spewed forth in vast quantities by volcanic activity. Oxygen, that vital breath of life for complex organisms, can be created by photosynthetic life, but it can also be formed through purely abiotic processes, when energetic ultraviolet light from a star violently splits water molecules apart in the upper atmosphere. Phosphine, another intriguing candidate, might indeed be produced by anaerobic bacteria, but it could also potentially form in the violent, high-pressure storms within the deep atmospheres of gas giants. Each of these gases, each of these potential bio-signatures, has at least one known, plausible abiotic pathway that, to some degree, muddies its interpretation, introduces a level of uncertainty. Dimethyl sulfide and its close chemical sibling, dimethyl disulfide, stand uniquely apart in this crucial regard. Their intricate chemistry, the very pathways of their formation, appear to demand specific biological processes, specific enzymatic machinery, that no known geological or purely physical process can replicate at the high, sustained concentrations observed. Furthermore, this molecule, dimethyl sulfide, possesses a remarkably short atmospheric lifetime. In Earth's dynamic, oxygen-rich atmosphere, dimethyl sulfide is a transient visitor. It breaks down, it is chemically dismantled, often within a matter of mere days. The relentless assault of sunlight, the eager embrace of oxygen, and the destructive power of hydroxyl radicals, those highly reactive molecular fragments, all conspire to tear it apart. This critical fact implies something profound. Any dimethyl sulfide we detect, whether on Earth or on a distant exoplanet, must be continuously, relentlessly replenished. On our planet, Phytoplankton bloom and die in intricate, predictable cycles, constantly pumping fresh supplies of this gas into the air. The very fact that we can measure it at all, even at Earth's relatively low concentrations, serves as undeniable proof that some powerful, ongoing process is making it constantly, tirelessly. Now, pause and truly imagine the implications. Imagine finding this exact gas, this biological whisper, on another world, a world so far away, at concentrations that are 10,000 times higher than what we detect on Earth. The mathematical conclusions, the logical deductions, become utterly unavoidable. Whatever source exists there, whatever process is at play, it must be incredibly, astonishingly powerful. Some profound mechanism, some ceaseless engine, is generating dimethyl sulfide or dimethyl disulfide faster, far faster, than the relentless forces of atmospheric chemistry can possibly destroy it. On Earth, our vast oceans teem with trillions upon trillions of phytoplankton, working around the clock, in a ceaseless, microscopic dance of life and death, to maintain our atmospheric concentrations. To produce the astonishing concentrations that the Webb telescope detected would, by all earthly comparison, require life on a scale so immense, so vast, that it is genuinely difficult, almost impossible, for our minds to fully comprehend. Remarkably, theoretical work, meticulously published even before the James Webb Space Telescope's groundbreaking observations, had predicted this exact scenario. Scientists, through intricate computer modeling, had explored hypothetical ocean worlds, possessing dense, hydrogen-rich atmospheres. They calculated that if life, specifically microbial life, were to exist and thrive in such environments, dimethyl sulfide would accumulate to much higher levels than it does on Earth. The very nature of a hydrogen atmosphere, they theorized, would significantly slow down the chemical pathways that typically destroy dimethyl sulfide. Microbes, they posited, could flourish in warm, surface oceans shielded from the harshness of space. And their waste products, including dimethyl sulfide, would, over immense spans of time, build up, slowly permeating the atmosphere above. These theoretical predictions, these prescient models, match the actual Webb observations almost perfectly, a convergence that sends a shiver of excitement through the scientific community. It is crucial to remember, of course, that this is still a theory, a powerful hypothesis supported by sophisticated models, not yet a confirmed, irrefutable fact. But the striking alignment between these theoretical predictions and the actual, meticulously obtained observations imbues scientists with a sense of cautious, yet profound, optimism. One distinguished researcher at Cambridge University articulated this sentiment eloquently, stating that, given everything currently known about this particular planet, a scenario in which it is an ocean world, absolutely teeming with diverse, vibrant life, represents the scenario that, quite simply, best fits all the available data. However, dear listener, caution remains the unwavering watchword in the rigorous world of scientific discovery. The imperative next step, the absolute bedrock of the scientific method, involves systematically and meticulously ruling out every conceivable alternative explanation, no matter how remote, no matter how seemingly unlikely it might initially appear. What if, just what if, some entirely novel, utterly unprecedented process, something we have never before considered, could somehow manufacture these very same molecules in such prodigious quantities? The quest for truth is a diligent one. When scientists speak of having 99.7% confidence, a figure that resonates with such precision, they are delving into the intricate, nuanced language of statistics. More specifically, what they are communicating is that the precise signal they detected, those distinctive absorption features in the starlight, possesses an infinitesimally small 0.3% chance of being nothing more than random noise, a spurious fluctuation in the vast cosmic background. In the formal, rigorous parlance of statistics, This level of certainty is termed 3 sigma. To help visualize what 3 sigma truly represents, consider a simple, familiar act: flipping a coin. If you were to flip a coin and, against all intuitive odds, get heads 10 times consecutively, you might begin to harbor a strong suspicion. You might, quite reasonably, start to suspect that the coin itself is somehow weighted, somehow rigged. That level of suspicion, that feeling of profound improbability, is roughly analogous to what 3 sigma certainty feels like in scientific terms. Now, escalate that scenario. Imagine flipping that same coin and miraculously getting heads not 10, but 20 times in a row. At that point, your suspicion would transform into an almost unshakable conviction. You would be absolutely certain that the coin was weighted, beyond any shadow of a doubt. That level of near absolute certainty, that profound statistical improbability, is what 5 sigma represents. The gold standard for claiming a truly revolutionary scientific discovery, a finding that reshapes our understanding, invariably sits at this 5 sigma level. At this exquisitely stringent threshold, the probability of error, of being wrong due to mere chance, plummets to an almost unfathomable degree, less than 0.0006%. To put that into perspective, it's like flipping a coin and getting heads 22 times in a row. Particle physicists, in their monumental quest for fundamental truths, rigorously employed this 5 sigma standard when they triumphantly announced the discovery of the elusive Higgs boson, that fundamental particle that gives all other particles mass. Astronomers, similarly, adhered to this demanding standard when they confirmed the existence of gravitational waves, those ripples in the very fabric of space-time, predicted by Einstein a century ago. For a discovery as utterly profound, as potentially paradigm-shifting, as the detection of alien life itself, nothing less than this unwavering 5 sigma certainty will, or indeed, should, suffice. Right now, this captivating, tantalizing discovery, this whisper of life from afar, rests firmly at the 3 sigma level. It is undeniably, incredibly exciting, a beacon of hope and curiosity. But it is, just as undeniably, not yet conclusive. There remains that slender, 0.3% chance of error, a tiny sliver of cosmic doubt that science, in its relentless pursuit of truth, must endeavor to eliminate. Here is a glimpse into the meticulous process by which this confidence level was calculated. The James Webb Space Telescope, with its unparalleled observational power, carefully gathered data revealing those distinct absorption features at specific telltale wavelengths. Scientists then embarked on a rigorous comparison, pitting this precious observational data against sophisticated computer models. One set of models assumed the unequivocal presence of dimethyl sulfide, or dimethyl disulfide, within the planet's atmosphere. Another, contrasting set of models assumed the complete absence of these specific molecules. The model that incorporated the presence of these sulfur compounds consistently provided a significantly, demonstrably better fit to the observed data. Statistical tests, meticulously applied, then revealed that the probability of obtaining such an exceptionally good fit by sheer chance, if these crucial molecules are not actually present in the atmosphere, equated to that minuscule 0.3%. But chance, dear listener, is not the sole concern that keeps scientists rigorously checking their work. Systematic errors, those insidious, subtle biases inherent in instruments or methodologies, can be equally deceptive, equally capable of fooling even the most sophisticated equipment. Perhaps the telescope's intricate calibration drifted ever so slightly over time. Perhaps minute, almost imperceptible thermal noise, generated within the instrument itself, inadvertently created false signals. Or perhaps, even more subtly, the star itself, the parent sun of this distant world, possesses unusual, as yet unknown properties that somehow mimic the distinct spectral signature of dimethyl sulfide. Scientists have, for many painstaking months, diligently explored and systematically checked for every single one of these possibilities. They leveraged the redundancy built into the Webb telescope, utilizing two different instruments, NIR-SPEC and MIRI, to observe the same phenomenon. Both instruments, independently, consistently saw the exact same signal, a powerful internal validation. They meticulously examined observations of other exoplanets, searching for similar anomalies, ensuring that this specific signature was genuinely unique to this particular ocean world. They developed and modeled dozens of alternative atmospheric compositions, exploring every conceivable abiotic chemical pathway. And yet, nothing else, no other combination of non-biological factors, fit the observed data as well, as elegantly, as compellingly, as the presence of these sulfur compounds. To truly reach that coveted 5 sigma certainty, to definitively declare a discovery, they require more data. Each observation window, each precious opportunity to watch the planet transit its star, lasts approximately 8 hours. So far, they have utilized 2 such windows, 2 fleeting glimpses. Scientists conservatively estimate that they will need at least 2 or 3 more, perhaps even more, to reach the necessary statistical threshold. This translates to an additional 16 to 24 hours of invaluable telescope time, meticulously spread across multiple transits. The planet, in its remarkably swift celestial dance, completes a full orbit around its star every 33 Earth days. This means that opportunities for observation, while precious, arise relatively frequently, a cosmic cadence for discovery. However, the James Webb Space Telescope is, by far, the most oversubscribed telescope in the entire history of astronomical observation. Thousands of brilliant astronomers, from every corner of our planet, compete fiercely for this incredibly valuable, limited observation time. Gaining approval for additional observation time requires a rigorous, highly competitive selection process where scientific merit is weighed against the immense demand. The lead researcher on this groundbreaking project has confirmed that their team has formally applied for this crucial additional observation time. A distinguished review panel, composed of leading experts, will meticulously decide whether the profound scientific implications, the sheer weight of this potential discovery, truly justifies the immense cost and the allocation of such a precious resource. If their application is approved, the definitive confirmation, the undeniable answer to humanity's oldest question, could potentially arrive within the next 12 months. That timeline, dear listener, places us potentially just one short year away from knowing, with a certainty that approaches the absolute, whether we have, at long last, truly detected alien life. One short year away from, perhaps, answering humanity's most ancient, most profound, and most awe-inspiring question, are we alone? But here, dear listener, is what makes this present moment, this delicate precipice of discovery, so utterly electric, so profoundly captivating. Even at 3 sigma, even with that minuscule sliver of uncertainty still lingering, we have undeniably, irrevocably, crossed a profound threshold. For the very first time in the entire annals of human history, we possess concrete, empirical data from another world, data that is, quite simply, easier to explain with the presence of life than without it. That in itself is a truly unprecedented, utterly momentous occurrence. It has never ever happened before. What then makes this particular world so exquisitely special, so uniquely poised to produce such a profoundly suggestive signal? The planet, this intriguing ocean world, orbits a star that is classified as a red dwarf. These celestial bodies are fundamentally different from our own bright, golden sun. They are significantly smaller, considerably cooler, and dramatically dimmer. This specific red dwarf, the parent star of our ocean world, possesses a surface temperature of approximately 384 degrees Celsius, a stark contrast to our Sun, which blazes fiercely at 500 degrees Celsius. Furthermore, this red dwarf contains only about 45% of our Sun's immense radius. Less mass, less heat, less light. But here lies the cosmic trick, the elegant compensation. This particular planet orbits its dim red star at a much closer proximity than Earth orbits our Sun. Our Earth, our comfortable home, sits a vast 93 million miles away from the Sun. This ocean world, by striking contrast, orbits its star at a mere 13 million miles. This places it an astonishing 167 times closer to its star, relative to the star's size, than Earth is to its Sun. This proximity, this intimate dance, matters far more than you might initially think. The intensity of starlight, the sheer amount of energy received from a star, meticulously follows what is known as the inverse square law. This fundamental law of physics dictates that if you double your distance from a light source, you receive only 1/4 of the light. Conversely, if you move 10 times closer, you receive 100 times more light. This ocean world orbits so remarkably close to its dim red star that, despite the star's inherent faintness, its relative dimness compared to our Sun, the planet ultimately receives roughly the same amount of stellar energy as Earth does from our much brighter Sun. Scientists refer to this delicate, life-sustaining balance as residing within the habitable zone. This is a meticulously defined region around any given star where, theoretically, a planet possessing the right kind of atmosphere could potentially maintain liquid water on its surface, that vital solvent and medium for life as we understand it. For our Sun, that comfortable, life-sustaining zone spans from approximately 90 million to about 140 million miles. For the cooler, dimmer red dwarfs, however, the habitable zone shifts dramatically inward, nestling much closer to the star, sometimes just a few million miles out. This crucial understanding, this precise mapping of habitable zones around different star types, has been rigorously confirmed by decades of meticulous astronomical observations and sophisticated climate modeling. Yet, temperature on a planet is not merely a function of its distance from its star. The presence and composition of an atmosphere fundamentally alter everything. A planet enveloped by a thick atmosphere possesses the remarkable ability to trap heat, much like a cozy blanket, through what we call the greenhouse effect. Carbon dioxide and methane are particularly adept at this thermal embrace, exquisitely efficient at absorbing and re-radiating infrared heat. Water vapor, too, plays a crucial role in this atmospheric thermal regulation. The right, delicate mix of these gases can effectively keep a world warm and hospitable, even if it is situated relatively far from its parent star. Venus, our scorching planetary neighbor, serves as a stark, dramatic demonstration of this principle, albeit gone catastrophically wrong. Despite orbiting closer to the Sun than Earth, Venus would, in fact, be a significantly cooler world if not for its crushing, immensely dense carbon dioxide atmosphere. Instead, its surface temperatures soar to an infernal 470 degrees Celsius, hot enough to melt lead. This distant ocean world, we have observed, possesses a hydrogen-rich atmosphere. Hydrogen, while a potent greenhouse gas in sheer volume, is inherently less efficient at trapping heat, molecule for molecule, than carbon dioxide. However, it compensates for this lower efficiency with its sheer, overwhelming volume. Theoretical models suggest that this planet's atmosphere might, astonishingly, represent up to 6% of the planet's total mass. For a profound comparison, consider our own Earth. Our atmosphere constitutes less than 1/1,000,000th of our planet's entire mass. That immense quantity of hydrogen, that colossal atmospheric envelope, creates an undeniably strong greenhouse effect, even with hydrogen's individual lower efficiency per molecule. The sheer weight and density of it traps an extraordinary amount of heat, making liquid water a distinct possibility. But here, dear listener, comes a significant complication, a potential peril embedded within this intimate cosmic dance. The very closeness to its star that allows for the possibility of liquid water also brings with it inherent dangers. Red dwarf stars, as a class, are known to be far more volatile, far more tempestuous than our own Sun. They unleash powerful, sudden bursts of radiation and streams of highly charged particles known as stellar flares, which violently blast any nearby planets. These flares, these cosmic tantrums, can, over millions of years, relentlessly strip away planetary atmospheres, eroding them particle by particle. They also bathe planets in intense ultraviolet and X-ray radiation, wavelengths of light that are profoundly destructive to complex organic molecules and can effectively sterilize planetary surfaces, making the emergence or survival of life incredibly challenging. Yet, despite this inherent stellar violence, this distant ocean world appears to have remarkably retained its atmosphere. Observations clearly indicate the abundant presence of hydrogen, methane, and carbon dioxide. If the star were constantly, relentlessly stripping its atmosphere away, we would expect to see clear, unambiguous signs of atmospheric loss, an outflow of gas into space. The very presence of these relatively heavy molecules, like methane and carbon dioxide, suggests that the planet has managed to cling to its gaseous envelope for a considerable, perhaps even billions of years, span of time. Perhaps its immense gravity, being 2.6 times the size of Earth, plays a crucial role anchoring the atmosphere more firmly. Perhaps the atmosphere itself is simply so thick, so massive, that it can effectively weather these stellar storms, acting as a colossal shield. Or, and this is a more poignant thought, perhaps we are witnessing something truly special, a fleeting moment in cosmic time, a planet caught in a brief, precious window of habitability, a temporary respite before its atmosphere is, inevitably, destined to disappear. The star itself, this dim red dwarf, is estimated to be approximately 2.4 billion years old. To put that into perspective, our Earth, our ancient home, is roughly 4.5 billion years old. This star system, then, is approximately half the age of our own solar system. It is young enough that the planet may still be geologically active, with internal heat driving volcanic processes or plate tectonics, which can be crucial for replenishing atmospheric gases and cycling nutrients. Yet, it is also ancient enough, venerable enough, that any life, given the right conditions, would have had ample, profound stretches of time to evolve, to adapt, to diversify, and to perhaps leave its chemical signature in the sky. Now, consider what happens when you combine all these intriguing factors: the dim, red star, the close orbit, the hydrogen atmosphere, the immense gravity, with perhaps the strangest, most peculiar feature of this distant world. One full orbit, one complete year, on this planet, takes a mere 33 Earth days. That means, to truly grasp the temporal difference, a year there lasts just over a single Earth month. Imagine, if you will, celebrating your birthday 33 times faster than you do now. By the time you reached your 30th birthday, according to Earth's leisurely calendar, you would, in a sense, be over 1,000 years old by this planet's measure. But this extraordinary orbital speed, this rapid celestial dance, carries profound consequences, consequences that ripple through and profoundly influence every single aspect of the planet's behavior, its climate, and its potential for life. First, let us contemplate the concept of seasons. On Earth, our familiar seasons occur primarily because our planet's rotational axis is tilted by approximately 23 degrees relative to our orbital plane. When the northern hemisphere, for instance, tilts towards the Sun, we experience the warmth and abundance of summer. 6 months later, as our planet continues its stately journey around the Sun, the northern hemisphere tilts away, ushering in the chill and quietude of winter. This ocean world, however, is thought to have a minimal axial tilt, meaning that seasons, as we experience them, the slow, predictable progression of spring, summer, autumn, and winter, would simply not happen in the same way. Instead, any significant climate variation, any shift in its planetary conditions, would arise directly from the orbit itself, from its journey around its star. And here is where things become truly, profoundly interesting. The planet's orbit is not, as one might assume, a perfectly circular path. Scientists meticulously measure this deviation from a perfect circle using a numerical value called eccentricity. Earth's orbit, for instance, possesses an eccentricity of a mere 0.017, which is remarkably close to a perfect circle. This distant ocean world, however, boasts an eccentricity of approximately 0.09, which is over 5 times more elliptical than Earth's orbit. This crucial detail, this pronounced elliptical shape, has been rigorously confirmed through precise, painstaking measurements of its orbital timing, tracking its exact position as it transits its star. What this pronounced eccentricity means, in practical terms, is that the planet's distance from its parent star changes quite significantly throughout the course of each orbit, each rapid 33-day year. At its closest point to the star, a celestial moment known as periastron, the planet is situated approximately 12% nearer to the star than it is at its farthest point, or epistron. That 12% difference might not sound like a monumental shift, but the inverse square law, that fundamental principle governing light intensity, powerfully amplifies this seemingly small difference. As a direct consequence, the planet receives an astonishing 43% more starlight, 43% more incoming energy, at its closest approach compared to its farthest distance. Imagine, if you possibly can imagine, if Earth's delicate, intricate climate swung with such breathtaking, violent intensity. Every few weeks, a mere fraction of a month, our planetary temperatures would not just fluctuate gently, but would dramatically spike and then precipitously crash, caught in relentless, almost brutal cycles. Any liquid water gracing the surface of such a world would be subjected to constant, agonizing freeze-thaw cycles. This scenario, this rapid, profound oscillation, introduces a fundamental, almost insurmountable stability problem for life as we currently understand its intricate requirements. Life, in its exquisite complexity, particularly complex life, thrives within relatively stable temperature regimes. Extreme, rapid swings, such profound and frequent environmental chaos, make it incredibly challenging for complex biochemistry, for the delicate dance of proteins and enzymes, to establish itself, to find its rhythm, to maintain its integrity. Imagine a world where, at one fleeting point in its orbit, its vital water might freeze solid, locking all life into an icy prison. Then, just a few short weeks later, at another, closer point in its orbital path, that very same water might boil away into a searing, sterilizing steam. Organisms, to merely survive, would need to possess an almost miraculous resilience, capable of enduring both these crushing, diametrically opposed extremes within the span of a single, frantic month. On our Earth, we certainly have examples of extremophile bacteria, those tenacious, microscopic pioneers that can indeed handle remarkably wide temperature ranges. Some species, for instance, flourish and multiply in the scalding, superheated waters of boiling hot springs at temperatures that would instantly kill most other forms of life. Others, conversely, endure and even thrive in the frigid, bone-chilling depths of Antarctic ice, surviving temperatures far below freezing. Yet, to ask organisms to not just survive, but to actively adapt and thrive through both these diametrically opposed extremes, and to do so on a relentless, monthly schedule, presents a challenge of an entirely different, far more demanding magnitude. And yet, dear listener, the unmistakable signal of dimethyl sulfide, that intriguing chemical whisper of potential life, persistently echoes back to us. If life does indeed exist there, on this planet of furious, swift seasons, it has, with a resilience we can barely fathom, profoundly adapted to this chaotic, rhythmic dance of its elliptical orbit. perhaps the thick, cushioning hydrogen atmosphere. That immense gaseous blanket acts as a powerful buffer, effectively smoothing out these otherwise extreme temperature fluctuations, mitigating the most violent swings. Or perhaps, the resilient life forms their retreat, finding refuge in deeper, more stable waters during the most intense temperature spikes and crashes, patiently waiting for conditions to once again stabilize and become more clement. It is also quite plausible that the vast, deep oceans themselves, with their immense thermal inertia, their capacity to store and retain heat, possess enough inherent stability to prevent truly wild, catastrophic fluctuations in temperature, offering a sanctuary against the orbital madness. There is, however, another profound consequence, another intricate problem, inextricably linked to these incredibly fast orbits, to this intimate celestial dance. When a planet maintains such a close, tight embrace with its parent star, the gravitational forces at play become extraordinarily intense, almost overwhelming. The star, with its immense mass, exerts a significantly stronger gravitational pull on the side of the planet that is nearest to it, compared to the side that is farthest away. Over the immense, geological timescales of millions upon millions of years, this subtle yet relentless difference in gravitational pull generates immense internal friction within the planet, creating what are known as tidal forces. These ceaseless forces act as a slow, inexorable brake, gradually, relentlessly slowing the planet's rotation. Eventually, inevitably, the planet's rotation period becomes perfectly synchronized with its orbital period. At this point, the planet becomes tidally locked. One side, then, is condemned to perpetually face the star, bathed in eternal, unending daylight. Conversely, the opposite side is cast into a realm of permanent, ceaseless darkness, perpetually frozen in the star's shadow. Scientists strongly suspect that this ocean world, given its close proximity to its red dwarf star, is indeed tidally locked, though this remains, for now, a theoretical conjecture unconfirmed by direct observation. If this hypothesis proves true, the implications for habitability are stark and dramatic. The dayside, perpetually illuminated, would be scorching hot, an inferno of endless sun. The night side, conversely, would be frozen solid, an expanse of eternal, crushing ice. Only a narrow, precarious twilight band, a slender ring or terminator, region situated precisely between these two extreme hemispheres, might manage to maintain temperatures that are, for at least some forms of life, suitable for the persistence of liquid water. Wind, driven by the colossal temperature differential, would howl relentlessly across this boundary, as superheated air from the dayside surges and rushes with incredible force to fill the frigid, low-pressure void of the night side. Weather patterns on such a world would be utterly alien, profoundly unlike anything we have ever witnessed or experienced on our own Earth. But what if, once again, the immense, thick hydrogen atmosphere fundamentally alters this game? Computer models, intricate simulations of planetary climates, suggest that such a dense atmospheric envelope could possess the remarkable capacity to transport heat from the scorching dayside to the frigid night side with astonishing efficiency. This atmospheric heat transfer could, in turn, create significantly more habitable conditions, extending the realm of potential life across much larger portions of the planet's surface, rather than confining it solely to a narrow twilight zone. However, without the ability to directly observe the planet's surface, scientists can, at present, only estimate these complex effects, relying on the elegant, yet still theoretical, dance of their computational models. What they know for certain, however, is that this world, in terms of its day, night cycles, and its fundamental distribution of light and heat, is unequivocally nothing like Earth. How, then, does a planet of such prodigious size, a world approximately 2.6 times the radius of Earth, manage to maintain conditions that could, potentially, support life? This planet is, by earthly standards, truly massive. Its sheer volume, for instance, is over 17 times that of our home world. If you could, somehow, stand upon its surface, assuming such a solid surface even exists, the gravitational pull would be immense, crushing you with a force approximately 2.5 times Earth's strength. Every single step you attempted to take would feel as though you were simultaneously carrying another entire copy of yourself on your back. A constant, profound burden. This colossal mass, this immense gravitational heft, has been rigorously confirmed through precise, painstaking measurements of the planet's mass and size, meticulously derived from the intricate laws of orbital mechanics. But this very size, this immense scale, presents a profound problem, a cosmic riddle. Planets this large, planets that dwarf Earth in this manner, typically do not resemble our familiar rocky world. Instead, they usually bear a striking resemblance to Neptune, our own solar system's distant, icy giant. Our solar system, in its elegant architecture, presents us with a clear dichotomy: four relatively small, dense, rocky planets in the inner system, and four colossal, less dense gas or ice giants in the outer reaches. There is, strikingly, nothing in between. This enigmatic ocean world, however, sits precisely in that perplexing gap, a cosmic anomaly. Planets like this are affectionately, yet scientifically, termed sub-Neptunes. They are fundamentally bigger than Earth, yet considerably smaller than Neptune. We have, to date, discovered thousands upon thousands of these intriguing sub-Neptunes orbiting other stars, but we possess not a single one within our own solar system to study up close, to probe its secrets. Here, then, lies the profound mystery. We simply do not yet know, with definitive certainty, what these sub-Neptunes are truly made of. Are they, perhaps, essentially rocky planets that have, through some unknown mechanism, managed to capture and retain enormous, thick atmospheres? Are they, conversely, icy worlds, akin to a miniature Neptune, that simply never accreted enough mass to swell into full-fledged gas giants? Or are they, most intriguingly, something else entirely, a wholly new, previously unimagined class of planet that simply does not exist within the familiar confines of our own solar system? The answer to this fundamental question, the precise composition and internal structure of these worlds, is absolutely critical, for it directly determines whether life, as we comprehend it, could possibly survive, let alone thrive there. The planet's density offers crucial clues, acting as a cosmic Rosetta Stone. Earth, our home, possesses an average density of 5.5 grams per cubic centimeter. This high density is a direct consequence of our planet being predominantly composed of dense iron and various silicate rocks. Neptune, by contrast, exhibits a much lower average density of 1.6 grams per cubic centimeter. This lower density reflects Neptune's primary composition. It is largely a volatile world, consisting mostly of water, ammonia, and methane ices, all wrapped within a vast, turbulent envelope of hydrogen and helium gas. This distant ocean world, our subject of fascination, has an average density of 2.67 grams per cubic centimeter, placing it squarely, intriguingly, right between Earth and Neptune. This intermediate density immediately suggests a possible, compelling internal structure. One leading possibility posits that the planet possesses a substantial rocky core, perhaps 3 to 4 times the mass of Earth's core. Above this dense, rocky heart, scientists theorize, lies a colossal mantle of high-pressure ice. This is not the familiar, crystalline ice you might find in your freezer, but rather exotic forms of ice that solidify under extreme, crushing pressures and, remarkably, can remain solid even at surprisingly high temperatures. Above this enigmatic ice mantle, there might be a vast, deep layer of liquid water, an ocean of unimaginable scale, and above that, wrapping the entire world, a thick, pervasive atmosphere primarily composed of hydrogen and helium. This intricate structure, it must be emphasized, is purely theoretical. an elegant model meticulously constructed from the observed measurements of the planet's mass and density. At this precise moment in our scientific journey, no one knows for certain. This compelling model, however, leads directly to the fascinating concept of Haitian worlds. The very name itself is a clever, evocative portmanteau combining hydrogen and ocean. The central idea behind Haitian worlds suggests that planets, even those significantly larger than Earth, but which possess dense hydrogen atmospheres and vast, deep liquid water surfaces, could, against conventional wisdom, be perfectly habitable. The immense hydrogen atmosphere, in this scenario, would efficiently trap heat through a powerful greenhouse warming effect, creating conditions conducive to liquid water. And that liquid water, in turn, would provide the essential medium, the vital solvent for life to emerge, to evolve, and to thrive. Microbes, tiny, single-celled organisms, could potentially float and proliferate within these colossal Haitian oceans, much like our own phytoplankton drift and flourish in Earth's familiar seas. However, critics of the Haitian world hypothesis raise valid, important questions, pointing out potential problems with this alluring picture. At the crushing surface pressures that are expected on such a massive planet, water might not, in fact, remain in a stable liquid state. It might, instead, exist in a supercritical state, a bizarre and enigmatic phase where the fundamental distinction between liquid and gas completely breaks down. Imagine water that possesses the fluidity and flow of a liquid, yet simultaneously exhibits the density and expansive properties of steam. This supercritical state, in-between phase, begins to manifest above 374 degrees Celsius and beyond 221 times Earth's normal atmospheric pressure. If the planet's surface temperature or pressure were to exceed these precise thresholds, stable, distinct liquid oceans, as we understand them, simply could not exist. Some scientists, based on their climate models, argue that this world might, indeed, be too hot for liquid water. Their simulations suggest that with its thick hydrogen atmosphere and the substantial amount of starlight it receives, surface temperatures could potentially soar to over 500 degrees Celsius. At such infernal temperatures, any water present would unequivocally exist either as a supercritical fluid or as superheated steam. The surface itself, in this scorching scenario, might be a vast, turbulent expanse of molten rock, a fiery magma ocean, all wrapped within that dense hydrogen blanket. If this grim scenario proves true, then the compelling dimethyl sulfide signal, that whisper of life, would necessitate an entirely different, non-biological explanation, a profound reinterpretation of the evidence. But, as with many complex scientific questions, other models tell a distinctly different, more hopeful story. These alternative simulations suggest that if extensive clouds were to form high in the planet's upper atmosphere, these clouds could, crucially, reflect enough incoming starlight back into space to keep the surface significantly cooler, maintaining conditions where liquid water could persist. If the planet's albedo, its measure of reflectivity, were to exceed 90%, reflecting away most of the incoming stellar energy, then liquid water could, indeed, be maintained. However, whether such extensive, highly reflective clouds can genuinely form in the complex chemistry of hydrogen-rich atmospheres remains a significant, open question, as cloud formation processes in such alien environments are fundamentally different from those on Earth. What, then, makes the curious absence of certain molecules, not just their presence, an equally crucial and compelling clue in this cosmic detective story? Consider Earth's vast, life-filled oceans. They teem with an almost unimaginable 25 trillion individual phytoplankton. These microscopic, single-celled organisms drift and proliferate in the sunlit surface waters, generally the top 600 feet or so, where sunlight can penetrate, providing the energy for photosynthesis. Using this light, They tirelessly convert carbon dioxide and solar energy into their own sustenance, their own chemical energy. In doing so, they collectively produce roughly half of all the oxygen we breathe, making them the silent, unseen architects of our breathable atmosphere. They also form the fundamental base of the entire oceanic food chain, supporting all other marine life. And, as we have discussed, they are the primary architects of dimethyl sulfide, the very molecule whose scent you encounter when you visit a vibrant, living beach. That distinctive, evocative smell in the air, that unique aroma of the seaside, comes in large part from these tiny, industrious beings. Phytoplankton, in their intricate cellular machinery, create a compound called dimethylsulfonneopropionate, or DMSP, primarily to regulate their internal salt balance. It acts as an osmolyte, a molecular tool that helps them cope with the inherent saltiness of seawater, maintaining cellular integrity. When these phytoplankton, in their natural life cycle, die, or when they are attacked and broken down by marine bacteria, specific enzymes within the ecosystem diligently break down this DMSP compound. One of the crucial breakdown products, one of the inevitable molecular results, is dimethyl sulfide. This gaseous byproduct then escapes from the ocean's surface and diffuses into the atmosphere at an astounding rate, globally contributing about 100 million tons per year. This entire process, from production to emission, is confirmed science, meticulously measured directly through atmospheric sampling campaigns and large-scale satellite observations. But, as previously noted, this molecule, dimethyl sulfide, does not linger long in Earth's dynamic atmosphere. It has a remarkably short lifespan. Hydroxyl radicals, those highly reactive molecular fragments, relentlessly attack it within a matter of days. Sunlight, with its energetic photons, ceaselessly breaks it apart, and oxygen, in its reactive nature, oxidizes it, gradually transforming it into sulfur dioxide, which then further converts into sulfuric acid. This sulfuric acid then forms tiny, microscopic particles, or aerosols. These aerosols, in a fascinating atmospheric feedback loop, act as cloud condensation nuclei, effectively seeding the formation of clouds. More clouds, in turn, mean more incoming sunlight is reflected back into space, thereby cooling the planet. Some scientists have even proposed that this entire sequence of events creates a remarkable feedback loop. Warmer oceans lead to more vigorous production of phytoplankton. More phytoplankton, in turn, produce more dimethyl sulfide. More dimethyl sulfide then leads to the formation of more clouds. And more clouds, by reflecting sunlight, ultimately cool the planet. This intricate hypothesis, while widely discussed and compelling, remains for now unproven. Now, let us consider the profound implications of detecting dimethyl sulfide on an entirely different, distant world. The persistent presence of this signal unequivocally requires continuous production. Some powerful, ongoing process must be ceaselessly churning out this molecule, generating it faster than the relentless forces of atmospheric chemistry can possibly destroy it. On Earth, the combined, ceaseless efforts of trillions upon trillions of individual phytoplankton cells, those invisible architects of our atmosphere, barely manage to maintain atmospheric concentrations of dimethyl sulfide at a mere 1 part per billion. To reach the astonishing 10 parts per million concentration observed on this distant ocean world, we would require a production rate that is a staggering 10,000 times higher than what our Earth's oceans currently provide. What, then, could possibly achieve such an immense feat? One straightforward, albeit mind-boggling, option is simply a vastly greater abundance of phytoplankton, or similar microbial life. If the oceans of this distant world contain immensely more microbial life per unit volume than Earth's most productive seas, then the mathematical equation astonishingly balances. But this immediately begs the next crucial question: why would that be? Perhaps the unique combination of a hydrogen-rich atmosphere and vast, deep liquid water oceans creates exceptionally ideal, almost Edenic, conditions for colossal microbial blooms. Perhaps nutrients are far more abundant and readily available than on Earth. Or perhaps the lack of effective predators, the absence of a complex food web, allows these microbial populations to explode, unchecked, reaching densities that we can barely conceive. Another intriguing option involves fundamentally different biochemistry, an alien twist on life's molecular machinery. Perhaps organisms on this distant world produce dimethyl sulfide directly, not as a mere byproduct, but as a primary, intentional metabolic output. On Earth, phytoplankton produce DMSP for one specific reason: salt balance. And dimethyl sulfide simply happens as an incidental side effect, a molecular waste product. On another world, however, the evolutionary pressures, the selective forces, might be entirely different. Life there might utilize dimethyl sulfide as a crucial signaling molecule, a means of communication between cells. It might be an essential metabolic product, or even a primary waste product of their unique energy generation processes. Different evolutionary pathways, different cosmic pressures, could very well lead to entirely different uses, and thus, vastly different production rates, for the same fundamental molecule. There is also the critical question of the bacterial contribution. On Earth, bacteria play an absolutely enormous role in the crucial conversion of DMSP, the compound produced by phytoplankton, into dimethyl sulfide. Certain bacterial species have highly specialized enzymes dedicated to precisely this transformation. An ocean absolutely teeming with these specialized bacteria, diligently feasting on vast quantities of organic matter, could, in theory, produce truly enormous quantities of dimethyl sulfide. The fact that dimethyl disulfide, the chemical cousin, was also detected alongside dimethyl sulfide lends further support to this bacterial hypothesis. On Earth, dimethyl disulfide is primarily a product of bacterial metabolism, not directly produced by phytoplankton themselves. The smell these molecules produce, as you might guess, is quite strong and to many human noses, rather unpleasant. At high concentrations, dimethyl sulfide reeks distinctly of rotting vegetables, or perhaps the decaying scent of seaweed that has been left too long on a hot beach. Some individuals describe it as garlicky or intensely sulfurous. If you could somehow miraculously visit this distant ocean world, and somehow manage to breathe its hydrogen-rich atmosphere, assuming, of course, that the hydrogen itself didn't immediately prove fatal, the stench, the overwhelming aroma, would likely be an experience beyond anything you have ever encountered, an olfactory assault of truly epic proportions. Imagine standing downwind of a colossal, planet-spanning algae bloom, covering millions upon millions of square miles of ocean surface, all simultaneously releasing dimethyl sulfide into the air. That, dear listener, is what this planet's air might, quite literally, smell like. But the smell, fascinating though it may be, is ultimately the least interesting aspect of this profound discovery. The truly pivotal question is what this particular molecule, this sulfurous whisper, tells us about the tantalizing possibility of life itself. On Earth, we have, for many decades, meticulously searched, painstakingly experimented, and exhaustively modeled any non-biological pathway that could produce dimethyl sulfide at meaningful, detectable concentrations. And our collective scientific conclusion, to date, remains resolute: we have found nothing. Every known pathway, every efficient mechanism for its production, ultimately requires the intricate machinery of living cells. If the same fundamental truth holds true on this distant, alien world, then we are, quite literally, detecting life's undeniable chemical signature, beautifully, elegantly, written in the very starlight that travels across the vast cosmic expanse. How, then, could these concentrations be a staggering 10,000 times higher than those found in Earth's atmosphere? Earth's atmosphere, as we've noted, contains dimethyl sulfide at less than 1 part per billion by volume. If you were to collect an air sample directly above our oceans, you would indeed find it, but barely. The molecule, as discussed, breaks down with remarkable speed. Its average lifetime in our atmosphere is brutally short, often measured in mere days. One rigorous study, for instance, measured its lifetime at approximately 24 hours. Another found it to be closer to 48 hours. The precise variation depends on localized conditions, such as the intensity of sunlight, the ambient temperature, and the abundance of oxidizing chemicals in the air. But the fundamental conclusion remains unwavering and consistent across all studies: dimethyl sulfide simply does not last long in Earth's atmosphere. This is confirmed science, replicated and validated in countless atmospheric chemistry studies. 3 primary processes relentlessly destroy dimethyl sulfide on Earth. First, and perhaps most potently, hydroxyl radicals launch a fierce chemical attack. These radicals are highly reactive molecular fragments, possessing unpaired electrons, which makes them incredibly eager to react with almost anything in their path. They form when energetic ultraviolet light, emanating from the sun, violently breaks apart water molecules high in the upper atmosphere. Once formed, these relentless hydroxyl radicals will attack almost any organic molecule they encounter, greedily snatching away hydrogen atoms and thus breaking crucial chemical bonds. Dimethyl sulfide, with its 6 vulnerable hydrogen atoms, presents a ripe target for this chemical assault. Second, oxygen, that vital component of our breathable air, directly reacts with dimethyl sulfide. This reaction is generally slower than the rapid assault by hydroxyl radicals, but it is still chemically significant. Oxygen combines with the sulfur atom within the dimethyl sulfide molecule, creating sulfur dioxide as the initial step in a destructive chain. Eventually, this pathway leads to the formation of sulfuric acid. This is precisely why the burning of sulfur, containing fossil fuels, for instance, releases sulfur dioxide into our atmosphere, which then converts to sulfuric acid, falling back to Earth as damaging acid rain. The same fundamental chemistry, albeit at a natural, biological scale, happens to dimethyl sulfide as it drifts within our atmosphere. Third, sunlight itself possesses the power to directly break dimethyl sulfide apart. This process, known as photodissociation, occurs when an individual photon of light carries enough energy to literally snap chemical bonds. For dimethyl sulfide, ultraviolet wavelengths, specifically those between 200 and 300 nanometers, deliver precisely this kind of destructive energy. These energetic wavelengths carry enough punch, enough raw power, to break the carbon-sulfur bonds that hold the molecule together. The fragmented pieces then fly apart, destined to recombine with other atmospheric chemicals, effectively dismantling the dimethyl sulfide. Now, let us consider the profound differences when we transport this understanding to a hydrogen-rich atmosphere, such as that of our distant ocean world. Hydroxyl radicals would still form, but their production would be significantly less efficient. Hydrogen atmospheres inherently contain far less water vapor to break apart. Less water vapor, in turn, translates to fewer hydroxyl radicals being formed. Fewer radicals, consequently, means a significantly slower rate of destruction for dimethyl sulfide. Theoretical models suggest that the concentration of hydroxyl radicals in this ocean world's atmosphere might be a mere 1/10, or even 1/100th, of the levels found in Earth's atmosphere. The difference with oxygen is even more dramatic, far more stark. This ocean world, based on spectroscopic observations, possesses minimal, if any, detectable oxygen features. This crucial absence means that the direct oxidation pathway, that significant destructive route for dimethyl sulfide on Earth, simply would not operate there, or would operate at an incredibly diminished rate. Eliminating one major destruction mechanism automatically, profoundly, extends the molecule's atmospheric lifetime. photodissociation, the breakdown by sunlight, would still occur. The planet's parent star, though a red dwarf, still emits ultraviolet light, albeit generally less UV than our Sun. However, the immense hydrogen atmosphere itself might play a protective role, absorbing some of the damaging UV radiation before it penetrates to the lower altitudes where dimethyl sulfide would concentrate. Additionally, the detected methane and carbon dioxide in the atmosphere also absorb certain UV wavelengths, providing further layers of shielding. The net effect of all these factors is that dimethyl sulfide would experience significantly less photochemical stress, less destructive assault from high-energy light. Putting all these profound differences together, the conclusion is striking: dimethyl sulfide might genuinely survive 10 times longer, possibly even 100 times longer, than it does in Earth's atmosphere. Instead of lasting a mere 1 or 2 days, it might persist for weeks or even months. This dramatically transforms the requirements for its continuous production. If you only need to replenish the molecule every few weeks instead of every single day, you inherently require much less biological activity to maintain the same high atmospheric concentration. A factor of 10 increase in its lifetime effectively reduces the necessary production requirements by a factor of 10. If its lifetime is 100 times longer, then you need only 1/100th of the production rate. But here, dear listener, is the crucial catch, the undeniable truth: even with a profoundly extended lifetime, even 100 times longer, you still require truly significant production to maintain concentrations of 10 parts per million. The math, in its relentless logic, is unavoidable. Something on this distant world generates dimethyl sulfide at rates that would utterly dwarf anything we observe on Earth, even accounting for atmospheric differences. The extended lifetime certainly helps to explain how the concentration can remain so astonishingly high. But it does not, in any way, eliminate the fundamental need for an incredibly powerful, persistent source. Scientists are currently engaged in a meticulous effort to precisely pin down these exact lifetime numbers through detailed, complex atmospheric modeling. They carefully input the observed concentrations of methane, carbon dioxide, and hydrogen. They calculate the intricate photochemistry reaction by reaction, painstakingly tracking how each molecule interacts with others. They estimate the precise ultraviolet flux from the parent star, and they model the temperature and pressure at different altitudes within the atmosphere. The ultimate result of this intensive computational effort is a precise prediction of dimethyl sulfide's lifetime under those very specific, alien conditions. Early models, preliminary as they are, suggest lifetimes ranging between 10 and 100 days, a significant extension. However, the uncertainty in these early estimates remains, for now, quite large. What then could possibly explain these compelling signals without invoking the presence of life at all? Not everyone in the scientific community, quite rightly, believes that the dimethyl sulfide signal unequivocally points to biology. A growing number of astute scientists point to an alternative, equally fascinating, and potentially profound explanation. What if this world, despite being christened an ocean world, possesses no liquid water oceans at all? What if, instead, its surface is a vast, turbulent expanse of molten rock, a true magma ocean, all wrapped within that dense, suffocating hydrogen atmosphere? Such magma oceans, under specific conditions, could potentially produce some of the very same chemical signatures that we might otherwise associate with living oceans. This alternative explanation, this intriguing hypothesis, stems from detailed climate modeling published in early 2024, a testament to the dynamic, evolving nature of scientific inquiry. Here is how such magma oceans might, in theory, operate. The planet, as we know, receives a substantial amount of starlight, despite orbiting a relatively dim red dwarf. This, combined with the incredibly thick hydrogen atmosphere, creates a powerful, almost runaway greenhouse effect. Even though hydrogen itself is not as individually efficient as carbon dioxide at trapping heat, the sheer volume of it creates immensely serious warming. Models suggest that under these specific conditions, surface temperatures could, quite plausibly, exceed a searing 800 degrees Celsius. This, again, is theoretical, based on meticulous energy balance calculations and the well-established properties of known atmospheric gases. At such infernal temperatures, rock, as we understand it, would undeniably melt. Granite, for instance, typically melts around 200 degrees Celsius. Basalt, a common volcanic rock, melts at around 100 degrees Celsius. However, rocks are not simple, uniform substances, they are complex mixtures of various minerals. Some minerals, indeed, melt at significantly lower temperatures. A planetary surface maintained at a continuous 800 degrees Celsius would not necessarily be entirely, uniformly molten, but it could certainly feature widespread, flowing lava rivers, vast, bubbling lava lakes, and extensive molten regions covering substantial fractions of its surface. Picture, if you will, Jupiter's incredibly volcanic moon, but scaled up to an astonishing 2.5 times the size of Earth, a world perpetually consumed by fire and brimstone. Magma, molten rock, interacts with overlying atmospheres in incredibly complex and dynamic ways. Volcanic gases, under immense pressure, bubble up and escape through the molten rock, venting into the atmosphere. These gases typically include water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide, that distinctive rotten egg smell often associated with volcanic activity. When hydrogen sulfide, in particular, enters a hydrogen-rich atmosphere, especially at high temperatures, a complex cascade of chemistry can occur. Hydrogen sulfide can react with carbon, containing molecules to form various organic sulfur compounds. Laboratory experiments have, in fact, successfully demonstrated this. The yields, the amounts produced, are typically low, but continuous, vigorous volcanic outgassing, operating over immense timescales, could potentially maintain a steady, albeit low-level, production of these compounds. One dedicated research team meticulously ran the numbers, creating sophisticated models. They simulated a planet with a magma surface, a dense hydrogen atmosphere, and volcanic outgassing rates that were similar to, or even exceeding, Earth's most volcanically active periods. Their model, indeed, managed to produce dimethyl sulfide through purely abiotic chemistry, without any life involved. However, the concentrations they achieved, the amounts produced, fell significantly short, by factors of 10 to 100, compared to the actual observations made by the James Webb Space Telescope. They could, certainly, make dimethyl sulfide without life, but they simply could not make enough of it. The persistent gap between their model's output and the observed concentrations strongly suggests that biology might still be necessary to bridge the difference. However, it does not definitively rule out the possibility of uniquely enhanced volcanic processes, perhaps operating under conditions we do not yet fully understand or can accurately simulate. There is another crucial clue, another piece of the cosmic puzzle, that lends weight to the magma ocean hypothesis: the mysterious absence of ammonia. On Earth, nitrogen-rich atmospheres, when exposed to energy sources like lightning or solar radiation, can produce ammonia, a simple compound of nitrogen and hydrogen. Ammonia is also, notably, a common byproduct of life. Many bacteria, for instance, generate ammonia as a waste product of their metabolism. Theoretical models predict that a truly habitable ocean world, teeming with life, should, in fact, possess detectable levels of ammonia in its atmosphere. Yet, observations of this distant ocean world consistently show no trace, no spectral signature, of ammonia. This absence of ammonia has been rigorously confirmed through meticulous spectroscopic analysis. Magma ocean models, fascinatingly, provide a natural and elegant explanation for this missing ammonia. Nitrogen, under the high pressures and temperatures found in molten rock, has a tendency to dissolve into the magma. The technical term for this phenomenon is nitrogen partitioning into the melt face. If the planet's surface is indeed a vast, molten expanse, atmospheric nitrogen would be efficiently absorbed and locked away within the magma. This process would effectively deplete ammonia from the atmosphere. You would, therefore, end up with a planet that has its nitrogen locked firmly within its surface, rather than freely floating in the air as part of its atmospheric envelope. This explanation, this elegant solution, matches the observations of missing ammonia perfectly. Conversely, ocean world models, those that posit a surface of liquid water, struggle significantly with the missing ammonia. If liquid water exists at the surface, nitrogen should, theoretically, remain largely in the atmosphere, not dissolve into a molten interior. Ammonia should then readily form through various chemical reactions and, crucially, through biological processes. Its absence, therefore, becomes a perplexing puzzle within the ocean world framework. Some scientists argue that perhaps certain specific metabolic pathways, unique to alien life, could consume ammonia as rapidly as it forms, effectively keeping its atmospheric concentration near zero. But this requires assuming very special, unique biological conditions. The magma ocean explanation, by contrast, is far simpler. It requires no specialized biology, just the fundamental, well-understood principles of basic chemistry and geochemistry. However, magma ocean models face their own significant challenges. They struggle, for instance, to adequately explain the abundant methane that has been unequivocally detected in the planet's atmosphere. Methane, a relatively fragile molecule, should not, in theory, be stable at the incredibly high temperatures predicted for a magma ocean surface. It tends to break down efficiently into elemental carbon and hydrogen at temperatures above approximately 700 degrees Celsius. To maintain a significant 1% concentration of methane in the atmosphere would require either an extraordinarily vigorous, continuous production source or significantly cooler atmospheric temperatures than the magma ocean models typically predict. Either of these options creates substantial problems for the overall viability of the magma ocean hypothesis. The scientific debate, then, continues with vigor and intellectual passion. Some scientists, swayed by the elegant explanation for the missing ammonia, favor the magma ocean explanation. Others, conversely, lean strongly towards the ocean world explanation, primarily because it more readily accounts for the abundant methane and, crucially, the compelling dimethyl sulfide signal. Both camps, however, unequivocally agree on one fundamental point: more observations, more precise data, are desperately needed to break this deadlock, to tip the scales definitively in one direction or the other. The next round of James Webb Space Telescope observations might, with luck, detect other crucial molecules, additional chemical fingerprints, that could decisively settle the question. Certain specific chemicals, for instance, would only exist under the extreme conditions of a magma ocean, while others would only be present in an environment featuring vast quantities of liquid water. The universe, in its boundless wisdom, often provides the answers, if only we are patient and precise enough to ask the right questions and to listen to its subtle whispers. What if, in this grand cosmic puzzle, the planet does indeed possess water, but its atmosphere is far more alien, far more exotic, than anyone had previously dared to expect? Hydrogen, unequivocally, dominates this planet's atmosphere. Spectroscopic observations, those meticulous analyses of filtered starlight, consistently confirm this. The distinct absorption features, the precise manner in which starlight is filtered and absorbed, all point to the overwhelming presence of massive amounts of hydrogen and helium. This fundamental atmospheric composition, however, creates a profound, almost existential problem for life as we, here on Earth, intimately know it. Earth's atmosphere, our breathable air, is a delicate and specific mixture, approximately 78% nitrogen, 21% oxygen, and only trace amounts of other gases, with virtually no free hydrogen at ground level. Hydrogen, being incredibly light, is simply too buoyant. It readily escapes Earth's relatively weaker gravity and slowly drifts away into the vast emptiness of space. But this distant ocean world is far more massive. Its significantly stronger gravitational pull allows it to effectively hold onto its abundant hydrogen, clinging to it over immense timescales. Life on Earth, in its incredible diversity, evolved and flourished within a nitrogen-oxygen-rich environment. Our complex proteins, our intricate enzymes, our entire cellular machinery are all exquisitely adapted and finely tuned to this specific atmospheric chemistry. Oxygen, in particular, serves as the crucial, final electron acceptor in aerobic respiration, the incredibly efficient metabolic process that powers most complex, multicellular life on our planet. Without oxygen, life is generally limited to anaerobic metabolism, a less efficient process that works perfectly well for bacteria and some simpler organisms, but fundamentally restricts the potential for truly complex, multicellular life, the kind of life that might, one day, build civilizations. A hydrogen atmosphere, however, fundamentally changes everything. Hydrogen is not merely an inert gas, like nitrogen, which largely sits on the sidelines of atmospheric chemistry. Hydrogen is chemically active. It is a powerful reducing agent, meaning it readily donates electrons to other molecules. This is the precise opposite of oxidation, the process driven by oxygen. This fundamental difference profoundly affects what chemical reactions are even possible within such an atmosphere. Some reactions that proceed easily and efficiently in oxygen-rich atmospheres become incredibly difficult or even entirely impossible in hydrogen-rich ones. Conversely, other reactions, those that never happen on Earth, suddenly become energetically favorable and thus, chemically, quite plausible. But here, dear listener, is the truly surprising and remarkably hopeful part. Life might not only tolerate hydrogen atmospheres, but, in an unexpected twist of evolution, it could potentially thrive within them. Recent, groundbreaking laboratory experiments, meticulously conducted under controlled conditions, have specifically tested whether familiar Earth microbes, those tiny, ubiquitous single-celled organisms, could survive and even grow in environments composed of pure hydrogen. The results, astonishingly, shocked the very researchers who conducted them. Bacteria and yeast, organisms that in their natural terrestrial habitats would never, ever encounter a pure hydrogen atmosphere, grew perfectly fine when exposed to 100% hydrogen. This is not mere speculation, this is confirmed experimental data, rigorously published in peer-reviewed scientific journals, adding a crucial new dimension to our understanding of planetary habitability. These organisms did not necessarily grow faster, nor did they achieve greater biomass, but crucially, they did not die either. They demonstrated a remarkable, inherent adaptability. Hydrogen, it turns out, offers a wealth of metabolic opportunities, novel pathways for extracting energy. Some bacteria on Earth, for instance, are known as methanogens. These fascinating organisms utilize hydrogen as a primary energy source. They combine hydrogen with carbon dioxide in a process known as methanogenesis to produce methane, gaining vital energy from this reaction. These methanogens are not obscure anomalies, they thrive in diverse, oxygen-deprived environments, in the deep, scorching depths of hydrothermal vents on the ocean floor, in the murky, anoxic swamps and wetlands, and even, surprisingly, in the guts of many animals, including our own. Their very existence proves, unequivocally, that hydrogen-based metabolism is a viable, successful strategy for life. On a planet blessed with an abundant, atmospheric hydrogen supply, these specific metabolic pathways, these hydrogen-fueled biochemical engines, might very well come to dominate the entire ecosystem. The fundamental question then shifts: can complex organisms, beyond the single-celled microbial realm, evolve and flourish in such hydrogen-rich environments? On Earth, the monumental evolutionary leap from simple, single-celled life to complex, multicellular organisms broadly coincided with a dramatic and sustained rise in atmospheric oxygen levels. This pivotal event, affectionately termed the Great Oxidation Event, occurred approximately 2.4 billion years ago, when photosynthetic bacteria, those ancient, unseen architects, tirelessly filled our atmosphere with the oxygen byproduct of their metabolic processes. Within a mere few hundred million years, following this atmospheric transformation, complex, multicellular life began its grand emergence, diversifying and eventually paving the way for everything we see around us. While correlation does not definitively prove causation, the precise timing of these two momentous events is undeniably suggestive. Some scientists argue that oxygen's inherently high energy density, its remarkable ability to accept electrons and release substantial energy, makes it uniquely ideal for powering the energetic demands of complex life. Others, however, contend that any sufficiently energetic metabolic pathway, any robust method of extracting energy from the environment, could, in theory, suffice. Hydrogen metabolism, while providing somewhat less energy per individual reaction than oxygen metabolism, still provides a significant, viable source of energy. Perhaps, then, complex life evolves more slowly in hydrogen atmospheres, a more leisurely pace of diversification. Perhaps it takes on entirely different, alien forms that defy our terrestrial expectations. Or perhaps in such environments, complex life simply never progresses beyond microbial colonies, never achieves the multicellularity that we associate with macroscopic organisms. We simply do not know, because we possess only one singular example of life, our own, to meticulously study and understand. The hydrogen atmosphere enveloping this distant ocean world most likely originated during the planet's very formation. When planets coalesce and form from the swirling dust and gas of a protoplanetary nebula, they accrete, or gather, vast quantities of gas from their surrounding environment. Larger planets, by virtue of their greater gravitational pull, are inherently more efficient at capturing and retaining more of this primordial gas. If a planet grows massive enough, and does so quickly enough, it can, in a cosmic hurry, capture colossal amounts of hydrogen and helium before the intense radiation from its nascent star, as it ignites and begins to shine, blows away the remaining nebular gas. This ocean world, it is theorized, likely captured several Earth masses worth of hydrogen during its tumultuous formation. This concept, while theoretical, is robustly supported by sophisticated and well-established planet formation models. Over immense stretches of cosmic time, however, atmospheric escape, a slow but relentless process, gradually strips away this primordial hydrogen. High-energy particles, continually streaming from the star, physically knock individual hydrogen atoms out of the planet's upper atmosphere. These atoms, having gained enough speed and energy, can then overcome the planet's gravitational pull and drift away, forever lost into the vacuum of space. Red dwarf stars, as we've discussed, frequently erupt with powerful flares, which dramatically accelerate this atmospheric stripping process, making the challenge of retention even greater. Yet, despite these destructive forces, this world has, remarkably, retained its hydrogen atmosphere over billions of years. This longevity strongly suggests one of two possibilities. Either the planet is, by cosmic standards, relatively young, meaning it hasn't yet had enough time to lose a significant portion of its atmosphere. Or, alternatively, and perhaps more likely, its atmosphere is simply so incredibly thick, so profoundly massive, that it can effectively weather these relentless losses, acting as a vast, sacrificial shield. The sheer thickness, the immense mass, of the atmosphere is absolutely critical for habitability. A thin hydrogen atmosphere, for instance, would not be able to trap much heat, leading to a frozen world. A thick one, however, as we've seen, creates extreme, potentially crushing, greenhouse warming. The crucial challenge, then, lies in finding that precise, delicate balance. Too thin and any liquid water freezes solid. Too thick, and surface pressures become literally crushing, making life as we know it impossible. Models suggest that this particular planet currently sits tantalizingly near the very edge of habitability, a precarious balance. Small, seemingly minor changes in its atmospheric mass or composition could, quite easily, tip it from being potentially habitable to utterly uninhabitable. Why do some scientists, observing this intriguing world, believe it more closely resembles Neptune, our own distant ice giant, than it does our familiar Earth? Neptune, for reference, has a radius approximately 4 times larger than Earth's. Its mass is a staggering 17 times that of our home planet. Its atmosphere is predominantly composed of hydrogen and helium, with about 2% methane, which gives it its characteristic blue hue. Deep beneath this vast, swirling atmosphere lies a colossal mantle composed of a dense, slushy mixture of water, ammonia, and methane ices. Deeper still, at its very heart, lies a rocky core, perhaps slightly larger than Earth's. Crucially, Neptune is not a gas giant, in the same vein as Jupiter, which is almost entirely hydrogen and helium. Instead, it is classified as an ice giant, a world dominated by volatile compounds, by these various ices, rather than by hydrogen gas alone. This distant ocean world, despite being significantly smaller than Neptune, shares many striking characteristics with it. The planet's density, once again, tells a significant part of this story. Neptune's average density is approximately 1.6 grams per cubic centimeter. Our fascinating ocean world, as we know, measures 2.67 grams per cubic centimeter. Earth, the densest of the terrestrial planets, clocks in at 5.5 grams per cubic centimeter. The progression is clear, a gradual, intriguing transition. This planet falls squarely between Neptune and Earth in terms of its average density. Simple yet powerful. Calculations derived from these densities reveal that it must contain less rocky material than Earth, but significantly more rocky material than Neptune. But what, then, fills this intriguing gap? What constitutes the rest of its interior? Interior structure models provide crucial answers, offering a glimpse into the unseen depths. Scientists input the observed mass and radius of the planet, combining this data with established constraints from planetary science. We know, for instance, that rocky materials possess certain characteristic densities under various pressures. Water ice, under immense pressure, exhibits a different, predictable density, and hydrogen gas, when compressed to incredibly high pressures, also has its own distinct density. By meticulously testing different combinations of these materials, scientists can narrow down the range of plausible interior structures. This modeling, while theoretical, is rigorously grounded in the fundamental principles of physics and chemistry, principles that have been painstakingly established through countless laboratory experiments, and the profound insights of quantum mechanics. Most of these sophisticated models converge on a remarkably similar picture for this ocean world: a substantial rocky core, perhaps 1 to 3 times the mass of Earth's core. Above this dense core, they posit, lies a thick, colossal mantle of high-pressure ice and, crucially, possibly a vast, deep layer of liquid water. This enigmatic intermediate layer, this potential buried ocean, might be an astonishing 1,000 to 2,000 miles thick, an ocean of unimaginable depth and volume. Above that, wrapping the entire world, would be a hydrogen-helium atmosphere thousands of miles deep, gradually thinning out as altitude increases. This internal structure, this layered architecture, looks nothing like Earth's familiar rocky interior. Instead, it bears a striking resemblance to a smaller, slightly denser Neptune, a miniature ice giant with a bit more rock and a bit less gas. If this picture, this theoretical model, proves to be correct, then the planet, in any meaningful sense, possesses no solid surface upon which one could land a spaceship. Descending through its immense atmosphere, you would experience a continuous, gradual increase in pressure and temperature. Eventually, the hydrogen gas would become so incredibly dense that it would begin to behave like a liquid, a strange, metallic hydrogen fluid. Deeper still, the colossal ice mantle would begin. But there would be no sharp boundary, no distinct interface, no solid ground to touch down upon. The transition from the gaseous atmosphere to the dense, icy mantle would occur gradually, seamlessly, over hundreds of miles, a continuous gradient of pressure and phase. This, fundamentally, is how Neptune operates, and observations suggest this distant ocean world might function in a very similar manner. However, this interpretation, this vision of a mini Neptune, directly conflicts with the compelling detection of dimethyl sulfide. Neptune, in our own solar system, does not produce dimethyl sulfide. Its atmosphere is a complex soup of methane, ethane, acetylene, and other hydrocarbon compounds. No sulfur-based organic molecules, not a single one, have ever been detected there. If this distant world truly resembles Neptune in its fundamental chemistry and structure, why, then, does it exhibit a distinct chemical signature that Neptune so conspicuously lacks? One compelling possibility, which might reconcile these seemingly contradictory pieces of evidence, is the presence of a vast, liquid water layer, somehow sandwiched between the high-pressure ice mantle and the dense hydrogen atmosphere. At certain specific depths within this transition zone, the precise balance of pressure and temperature could allow for liquid water to exist stably. This water, however, would be profoundly different from Earth's oceans. It would not be in direct contact with the vacuum of space or the upper atmosphere. Instead, it would be trapped, encased beneath thousands of miles of hydrogen, a truly buried ocean. Yet, even in this isolated, extreme environment, it could still potentially host life. Microbes, floating and thriving within this subterranean ocean, could produce dimethyl sulfide. The gas, being lighter, would then slowly, laboriously, bubble its way up through the immense atmosphere, eventually reaching the altitudes where our powerful telescopes can detect it, a faint but persistent chemical beacon. Critics of this buried ocean scenario, however, raise legitimate problems. How, they ask, would life even begin in such a deeply buried, isolated ocean? On Earth, life is thought to have originated in shallow pools, rich in energy and chemicals, or perhaps near the dynamic, energy-rich environments of hydrothermal vents on the ocean floor, places where essential energy and raw chemical ingredients are concentrated. A deeply buried ocean, by contrast, would likely lack these crucial features. Energy sources would be incredibly scarce. Essential nutrients would be profoundly limited. The very genesis of life in such extreme, isolated conditions seems, at least from our terrestrial perspective, profoundly implausible. But, once started, perhaps through some unknown, unique mechanism, life might then be able to spread, adapt, and even thrive in such an environment, enduring the millennia in its subterranean realm. Another issue which adds to the complexity is the methane content. Neptune's atmosphere contains approximately 2% methane. This distant ocean world, by contrast, shows about 1% methane. On Neptune, methane is believed to originate from the planet's interior, slowly released through the processes of convection and atmospheric mixing. If this distant world truly resembles Neptune, its methane might have a similar geological source. However, ocean world models, those that posit a liquid water surface, explain methane differently. They propose a biological origin, with methanogenic organisms, like those found on Earth, tirelessly creating methane from the abundant hydrogen and carbon dioxide present in their environment. Both explanations, both the geological and the biological, are capable of fitting the observed methane concentrations, making it incredibly difficult to distinguish between them based on methane alone. The entire debate, then, ultimately boils down to a fundamental question: does this planet possess a distinct, stable surface and vast, deep oceans, or does it, conversely, entirely lack both, existing as a continuous gradient from gas to ice to rock? Spectroscopy, the art and science of analyzing light, can tell us with remarkable precision what chemical compounds exist in the planet's upper atmosphere. However, it does not directly, unequivocally, reveal what lies beneath that gaseous veil. We are forced to infer surface conditions from the atmospheric composition, but such inferences, while educated, can always be wrong. Multiple, competing explanations can often fit the same set of observational data. Breaking this degeneracy, this ambiguity, will require additional, even more precise observations that can probe deeper into the planet's enigmatic nature, providing definitive answers about its true, hidden depths. What happens when scientists meticulously examine the mysterious, almost perplexing, absence of a crucial atmospheric component, a molecule that, by all rights, should be there? The captivating concept of Haitian worlds, a term that has now entered the astrobiological lexicon, first emerged in 2021 from groundbreaking theoretical work led by visionary researchers at Cambridge University. They posed a deceptively simple, yet profoundly challenging, question: can planets that are significantly larger than Earth, yet still considerably smaller than Neptune, somehow manage to host vast, liquid water oceans, despite being enveloped by dense, hydrogen-rich atmospheres? Conventional scientific wisdom, for a long time, held that the answer was a resounding no. Hydrogen atmospheres, it was generally believed, would inevitably lead to runaway greenhouse effects, making planetary surfaces far too hot to sustain liquid water. However, meticulously detailed computer modeling, a powerful tool of modern science, began to reveal a different, more optimistic possibility. This was purely theoretical work, grounded in established principles of climate physics, pushing the boundaries of what we thought was possible. The key to this new understanding, the pivotal factor, lay in the intricate processes of cloud formation. High up in the planet's immense atmosphere, water vapor, abundant in such a world, could condense into extensive, highly reflective clouds. These clouds, crucially, would act as a colossal mirror, reflecting a substantial portion of the incoming starlight directly back into space before it could even reach and heat the surface. If enough of these reflective clouds were to form, they could, theoretically, keep the planet's surface cool enough to maintain liquid water, despite the potent greenhouse effect operating lower in the atmosphere. The sweet spot, the ideal balance, exists when cloud cover reaches approximately 50% to 70% of the planet's total surface area. Too little cloud cover, and the surface inevitably overheats, boiling away any water. Too much cloud cover, and insufficient starlight penetrates through to the surface to support photosynthesis, the primary energy source for most life on Earth, or to adequately heat the vast, deep oceans. Haitian worlds, according to these fascinating models, would likely possess surface pressures ranging between 100 and 1,000 times Earth's atmospheric pressure. That might sound incredibly crushing, almost unimaginably immense. However, it's worth remembering that Earth's own oceans already experience such pressures just a few miles down in their abyssal depths, and life, in its remarkable resilience, thrives in the deep ocean, enduring pressures that exceed 1,000 times surface levels. If life can comfortably handle those crushing pressures in Earth's deep oceans, perhaps it could similarly handle them at a Haitian surface, where the pressure comes from the immense weight of the overlying atmosphere rather than the crushing weight of a water column. Temperature, however, remains the trickier, more delicate constraint. Liquid water on Earth remains stable between 0 and 100 degrees Celsius at our planet's surface pressure. But at significantly higher pressures, water's boiling point increases, meaning it can remain liquid at higher temperatures. At 100 atmospheres of pressure, for instance, water boils at a scorching 3 to 11 degrees Celsius, rather than the familiar 100 degrees. At 200 atmospheres, the boiling point rises even further to 365 degrees Celsius. This remarkable property of water under pressure is rigorously confirmed through extensive laboratory pressure, temperature phase diagrams, fundamental charts of chemistry and physics. The absolute upper limit for liquid water exists at what is called the critical point of water. Above 374 degrees Celsius and beyond 221 atmospheres of pressure, water enters that bizarre, supercritical state where the distinction between liquid and gas completely merges, dissolving into a single, enigmatic fluid. Supercritical water possesses truly bizarre properties. It flows like a gas, yet it dissolves substances with the efficiency of a liquid. It could, potentially, support some form of life, but life as we intimately know it fundamentally relies on the distinct, separate properties of liquid water. Entering a supercritical state might, therefore, render habitability impossible for Earth, like biochemistry. Haitian models, in their optimistic projections, suggest that surface temperatures between 10 and 70 degrees Celsius are indeed possible under the right, carefully balanced conditions. That temperature range, importantly, is entirely compatible with life as we know it. Earth's hottest environments, such as the superheated waters surrounding deep sea hydrothermal vents, reach well over 100 degrees Celsius and yet host thriving, incredibly diverse bacterial communities. If Haitian oceans manage to stay cooler than even these extreme terrestrial environments, the plausibility of life existing there seems remarkably high. But, as emphasized, establishing and maintaining those specific temperatures requires an incredibly precise and delicate balancing act between the powerful greenhouse warming provided by the hydrogen atmosphere and the reflective cooling provided by extensive cloud cover. The hydrogen atmosphere, in these Haitian models, serves multiple crucial roles. It acts as a powerful greenhouse gas, preventing the planet from freezing solid. It also provides a significant protective shield against harmful, sterilizing space radiation. And, for certain types of organisms, it offers a direct metabolic fuel, a readily available energy source for hydrogen using microbes. However, it also presents a significant challenge. It effectively blocks much of the ultraviolet light that, on Earth, drives photosynthesis, the fundamental energy source for most surface life. Haitian life, therefore, might need to adapt to dimmer, redder light, the wavelengths that can more effectively penetrate the dense atmosphere. Given that red dwarf stars, the parent stars of these worlds, already emit most of their light in the red and infrared portions of the spectrum, this adaptation might not pose an insurmountable problem for alien photosynthesis. Nutrient availability poses another significant challenge. On Earth, the process of continental weathering, where rain and wind erode rocks, releases vital minerals into rivers, which then flow into our oceans. These minerals provide essential nutrients, the building blocks for marine life. Haitian worlds, however, might entirely lack continents, being true ocean planets. Without continental weathering, how would these crucial nutrients reach the vast, deep ocean? Perhaps vigorous volcanic activity on the seafloor, similar to Earth's hydrothermal vents, could tirelessly release these essential minerals directly into the water column. Or perhaps the ocean itself is constantly supplied from below, with chemicals slowly seeping up from the rocky mantle beneath. Either way, maintaining high biological productivity, and thus high concentrations of biosignature gases, would necessitate a robust and continuous supply of these vital nutrients. One particularly intriguing prediction of the Haitian models is that these worlds should exhibit very specific atmospheric signatures. They should, for instance, have high methane levels, potentially indicative of biological production. They should also show high carbon dioxide levels, originating either from volcanic outgassing or biological respiration. Detectable water vapor would, of course, be a given. And, crucially, they might harbor specific biosignature gases, such as dimethyl sulfide or methyl chloride. This distant ocean world, our subject of fascination, matches this predicted pattern almost perfectly. This remarkable alignment, this convergence between theoretical prediction and meticulous observation, is precisely what so profoundly excites researchers, fueling their cautious optimism and relentless pursuit of further data. How might these incredibly thick atmospheres, these colossal gaseous envelopes, create remarkably stable conditions for life? The concept of the greenhouse effect, unfortunately, often receives a rather bad reputation in modern discourse, largely due to urgent discussions surrounding climate change and the catastrophic potential of runaway greenhouse warming. However, it's crucial to remember that greenhouse effects, in and of themselves, are not inherently bad or destructive. In fact, they are precisely what make Earth, our own comfortable home, habitable in the first place. Without our planet's natural, delicate greenhouse effect, Earth's average global temperature would plummet to a frigid 8 degrees Celsius, well below freezing. Our vast oceans would freeze solid, transforming our vibrant blue marble into a lifeless, icy wasteland. Instead, the presence of these crucial greenhouse gases keeps us at a comfortable, life-sustaining average of approximately 15 degrees Celsius. This, dear listener, is fundamental atmospheric physics, rigorously confirmed and meticulously measured through decades of scientific inquiry. The mechanism is elegantly straightforward. Incoming sunlight, carrying its energy, passes relatively unimpeded through the atmosphere and warms the planet's surface. The warm surface, in turn, radiates this absorbed energy back upwards, but in the form of longer, wavelength infrared light, which we perceive as heat. Greenhouse gases, those special molecules in the atmosphere, possess the unique ability to absorb this outgoing infrared radiation, effectively trapping heat in the lower atmosphere, much like a cozy, insulating blanket. These gases eventually radiate this absorbed energy, but some of it is directed back downwards, towards the surface, creating a continuous warming effect. The more greenhouse gas present in the atmosphere, the more heat is trapped, and thus, the greater the warming effect. This relationship, while not perfectly linear, is remarkably predictable and well understood. On Earth, carbon dioxide and water vapor provide the bulk of our planet's natural greenhouse effect. Methane and nitrous oxide contribute smaller, but still significant, amounts. These specific gases work as greenhouse agents because their intricate molecular structures are uniquely capable of absorbing those specific infrared wavelengths. Not all atmospheric gases possess this crucial property. Nitrogen and oxygen, which together constitute the vast majority of our atmosphere, are largely transparent to infrared light. They simply do not contribute to greenhouse warming. Hydrogen and helium, similarly, are transparent. Therefore, to achieve a greenhouse effect, you need other, more complex molecules mixed into the atmosphere. This distant ocean world's hydrogen atmosphere, while massive, does not directly trap much heat on its own, given hydrogen's transparency to infrared. However, it contains approximately 1% methane and 1% carbon dioxide. That might not sound like a huge amount, but it is, in fact, profoundly significant. Earth's atmosphere, for comparison, contains only about 400 parts per million of carbon dioxide, which is a mere 0.4%. This distant planet, therefore, possesses a staggering 25 times more carbon dioxide than Earth. Methane, furthermore, is an even more potent greenhouse gas than carbon dioxide, molecule for molecule, meaning that a 1% concentration of methane provides a truly serious, powerful warming effect. Here is where the sheer presence of hydrogen, despite its infrared transparency, becomes incredibly important. The immense mass of the hydrogen atmosphere dramatically increases the pressure at the planet's surface. Higher pressure, in turn, means denser air, and denser air possesses a greater capacity to hold and retain heat. It also, crucially, slows down the escape of infrared radiation. Photons of infrared light, attempting to leave the planet and escape into space, get absorbed and emitted multiple times by the dense atmospheric molecules before they finally manage to make their way out. Each absorption-emission cycle delays the ultimate loss of heat, effectively extending the time heat remains trapped. The combined result is that even though hydrogen itself does not efficiently trap infrared, a thick, massive hydrogen atmosphere, through these pressure effects alone, still creates a profoundly significant greenhouse warming. Sophisticated models demonstrate that a hydrogen atmosphere containing just 1% carbon dioxide and 1% methane can effectively maintain surface temperatures warm enough for liquid water to exist, even on a planet that receives less total starlight than Earth. This crucial insight expands our traditional understanding of the habitable zone, pushing it outward from the star. Planets that would otherwise be considered too cold with Earth, like atmospheres, suddenly become warm enough, potentially habitable, with these dense hydrogen envelopes. It fundamentally flips conventional thinking about where, in the vast cosmos, we should direct our search for life. But, as always, there is a catch, a delicate balance that must be maintained. The greenhouse effect must be powerful, but it must not become too powerful. Venus, once again, serves as a stark, cautionary tale, a dramatic demonstration of what happens when greenhouse warming spirals catastrophically out of control. Venus receives approximately twice the amount of sunlight that Earth does and is enveloped by a crushing, immensely dense carbon dioxide atmosphere. Its surface temperatures, as we know, reach an infernal 470 degrees Celsius, a temperature hot enough to melt lead. On Venus, the greenhouse effect ran away, creating a positive feedback loop with no inherent braking mechanism. All of its surface water evaporated, creating even more greenhouse gas water vapor, which in turn created even more warming, leading to even more evaporation until the planet was baked dry and rendered utterly uninhabitable. This distant ocean world, our subject of inquiry, appears to sit right on the very edge of this precarious balance. Computer models consistently show that even small, seemingly minor changes in its atmospheric composition or its cloud cover could potentially push it over the brink, tipping it into runaway greenhouse territory. If, for instance, clouds were to fail to form or diminish significantly, surface temperatures would inevitably spike. Any remaining surface water would evaporate, further contributing to the greenhouse warming, initiating that irreversible positive feedback loop. Alternatively, if clouds were to become too thick, too pervasive, they could block too much incoming starlight. Surface temperatures would then plummet, any liquid water would freeze solid, and these frozen, icy surfaces would, in turn, reflect even more light back into space, creating even more cooling. This, too, could lead to another runaway process, but in the opposite, equally destructive, direction. The very fact that this planet, according to current observations, apparently maintains stable, life-permitting conditions, strongly suggests the presence of some inherent balancing mechanism, some powerful regulatory force. Perhaps, just perhaps, biological processes themselves actively help to stabilize the planet's climate. On Earth, as we've discussed, phytoplankton produce dimethyl sulfide, which then acts as a crucial seed for cloud formation. More warming in our oceans leads to more phytoplankton growth. More phytoplankton, in turn, produce more dimethyl sulfide. more dimethyl sulfide then leads to the formation of more clouds. And more clouds, by reflecting sunlight, ultimately lead to more cooling, a beautiful, self-regulating negative feedback loop. The exact same mechanism, this intricate biological thermostat, could very well be at play on this distant ocean world. If so, life there would not simply exist, life would actively, profoundly, regulate the planet's climate, making it habitable, maintaining its delicate balance against the forces of cosmic chaos. Why does the perplexing absence of ammonia split scientific opinion so sharply? Ammonia, a relatively simple compound of nitrogen and hydrogen and NH3, should, by all theoretical predictions and established chemical principles, be present in such an atmosphere. Multiple sophisticated models, simulating the conditions of a Haitian world, consistently predict its presence. Yet, as we've noted, meticulous observations by the James Webb Space Telescope show no trace, no spectral signature, of ammonia. This glaring absence has become one of the most intensely debated and enigmatic aspects of this planet's atmospheric composition. Ammonia formation is, fundamentally, expected in a hydrogen-rich atmosphere that receives energy from its parent star or from internal processes like lightning. In such an environment, nitrogen atoms, if present, readily combine with hydrogen to form ammonia. This is confirmed chemistry, not only observed in rigorous laboratory experiments, but also demonstrably present in the atmospheres of the gas giants within our own solar system. Jupiter, for instance, possesses abundant ammonia. So too do Saturn, Uranus, and Neptune. Wherever you find sufficient quantities of hydrogen and nitrogen together, coupled with enough energy to drive the necessary chemical reactions, ammonia invariably appears. Spectroscopic observations of these giant planets clearly show strong, unmistakable ammonia absorption features. No one questions whether ammonia is present in their atmospheres. The profound question, then, is why it is so conspicuously missing from this distant ocean world when, by all conventional understanding, it should be there. One compelling explanation invokes biological consumption. Some types of bacteria on Earth, for example, metabolize ammonia as a vital energy source. Nitrifying bacteria, a fascinating group of microorganisms, convert ammonia to nitrite, and then further to nitrate, diligently extracting energy from these chemical transformations. In an ocean absolutely teeming with such ammonia, consuming bacteria, atmospheric ammonia could, in theory, be removed or scrubbed from the atmosphere as rapidly as it forms. The vast ocean, in this scenario, acts as a powerful sink, constantly drawing ammonia out of the air. Atmospheric ammonia readily dissolves into water. The marine bacteria then consume it. As atmospheric ammonia is consumed, more dissolves from the air to replace what was lost. An equilibrium would then establish itself, where atmospheric ammonia concentrations remain near zero, perpetually consumed by the hungry microbes below. This explanation fits the ocean world hypothesis quite nicely, adding another layer of consistency. It requires the presence of life, but life is precisely what the methyl sulfide signal so strongly suggests. In this elegant interpretation, the two pieces of evidence, the presence of dimethyl sulfide and the absence of ammonia, mutually support each other. Biological metabolism, therefore, provides a consistent picture that explains both the puzzling presence of one molecule and the equally puzzling absence of another. However, it is important to acknowledge that this explanation inherently requires assuming that life already exists, which is precisely what scientists are ultimately trying to prove. This creates a potential risk of circular reasoning, a logical trap that scientists must diligently avoid. The alternative explanation, one that bypasses biology entirely, invokes purely abiotic chemistry, specifically the magma-ocean hypothesis. If the planet's surface is indeed a vast expanse of molten rock, nitrogen, as mentioned before, has a tendency to readily dissolve into this magma. experimental studies of volcanic systems, conducted under high temperatures and pressures, unequivocally show that nitrogen preferentially partitions or moves into the melt phase rather than remaining in the gas phase of the atmosphere. A magma ocean, therefore, would effectively suck nitrogen out of the atmosphere, locking it away in the molten interior. Without sufficient atmospheric nitrogen, ammonia simply cannot form, regardless of other conditions. In this interpretation, the absence of ammonia becomes compelling evidence for a magma ocean rather than a liquid water ocean. This explanation, therefore, fits the magma ocean hypothesis quite elegantly. It requires no life. It explains the missing ammonia through straightforward, well-understood chemistry. However, as we've discussed, this magma ocean hypothesis struggles significantly to explain the abundant dimethyl sulfide signal. While magma ocean models can, in principle, produce small, trace amounts of dimethyl sulfide through abiotic chemistry, whether they can produce enough to match the observed concentrations remains a profound question. The magma ocean hypothesis, in essence, explains one mystery while simultaneously creating or struggling with another. There is a third, less commonly discussed, possibility. Perhaps the spectroscopic observations, despite their incredible precision, simply miss the ammonia. Ammonia has distinct absorption features at specific wavelengths. If those particular wavelengths were not observed, or if the signal was obscured by noise or other atmospheric interference, ammonia could theoretically be present, but simply undetected. However, the James Webb Space Telescope observed multiple, broad wavelength ranges, and its instruments possess sufficient sensitivity to detect ammonia at concentrations that would be expected in a Haitian world. Furthermore, multiple independent research teams have meticulously analyzed the data, and all have consistently reached the same conclusion: no ammonia. The persistent absence of ammonia, therefore, forces scientists to choose between fundamentally competing scenarios. Either life actively consumes it, or a magma ocean actively absorbs it, or some third, as yet unknown process, efficiently removes it from the atmosphere. Each of these choices leads down a distinctly different path. For understanding the true nature of this enigmatic world, an ocean world teeming with life, a fiery magma ocean devoid of life, or something entirely unexpected and new. The scientific community, as a result, remains intellectually split. Some researchers strongly favor the biological explanation, finding it the most parsimonious. Others lean towards the magma ocean hypothesis, finding its chemical explanations more compelling for the missing ammonia. A third group, exercising admirable scientific caution, argues that the available data remains too ambiguous, too limited, to definitively choose between these intriguing possibilities. What they all universally agree on, however, is that more observations, more data, are desperately needed to break this deadlock, to bring clarity to this profound cosmic mystery. Imagine, if you can, an ocean where every single drop of water contains 1,000 times more individual microbes than even Earth's most productive, nutrient-rich seas. That is the astonishing scale, the sheer biological intensity that the observed dimethyl sulfide concentrations would demand. On Earth, phytoplankton, those tireless microscopic producers, primarily float and thrive in the sunlit surface waters, generally confined to the top 600 feet or so, where solar radiation can effectively penetrate. Below that relatively shallow layer, perpetual darkness reigns, and photosynthesis, the engine of most surface life, ceases entirely. On this distant ocean world, the same fundamental depth limit for light penetration would likely apply, unless some profound, unknown factor fundamentally changes the rules of physics and light. One possibility, which helps reconcile the numbers, is simply a vastly higher density of life. Earth's oceans, for instance, typically contain roughly 1 million bacterial cells per milliliter of seawater. That might sound like a significant number until you consider that a single gram of fertile soil can contain over 1 billion bacterial cells. Ocean water, by comparison to soil, is relatively sparse in microbial life. Perhaps this distant ocean, then, is more akin to a fertile, living soil, but in liquid form. Imagine incredibly dense bacterial mats, vast, living carpets, floating throughout the water column. Picture thick, pervasive biofilms coating every available submerged surface. Microbial density, in this scenario, could be literally 1,000 times higher than that of Earth's oceans. This, of course, is speculation, but the unforgiving math of the dimethyl sulfide signal strongly requires such immense biological productivity. Another possibility involves entirely different types of organisms, life forms that have evolved unique biochemical pathways. On Earth, dimethyl sulfide primarily originates from eukaryotic phytoplankton, organisms with complex cells containing nuclei and organelles. These relatively complex life forms evolved comparatively late in Earth's history, approximately 2 billion years ago. Before that, simpler, prokaryotic bacteria dominated the planet. Perhaps this distant ocean world hosts bacteria, or archaea, that produce dimethyl sulfide through entirely different, perhaps more efficient, metabolic pathways. Bacteria, with their rapid generation times, can evolve with astonishing speed, adapting to local environmental conditions within mere thousands of generations. An ocean absolutely teeming with such dimethyl sulfide, producing bacteria could, in theory, generate the observed concentrations with remarkable efficiency. The hydrogen-rich atmosphere itself, as we've discussed, opens up truly unique metabolic possibilities. Some Earth bacteria, those methanogens, combine hydrogen gas with carbon dioxide to produce methane, extracting energy from this reaction in oxygen-deprived environments. Perhaps similar organisms on this distant ocean world combine hydrogen with various sulfur compounds to produce dimethyl sulfide directly, not as a mere byproduct, but as a primary metabolic output. This would be a far more efficient pathway than Earth's, where dimethyl sulfide is an incidental side effect. Different evolutionary pressures, a different set of environmental circumstances, could readily lead to such specialized biochemical adaptations. Temperature also plays a crucial role. Warmer water, generally speaking, means faster metabolism. Chemical reactions, as a rough rule of thumb, approximately double in speed for every 10 degrees Celsius increase in temperature. If this distant ocean world's surface waters average, say 30 degrees Celsius, compared to Earth's average ocean temperature of about 4 degrees Celsius, then biological reactions would proceed approximately 8 times faster. An 8 times faster metabolism, compounded by potentially higher cell density, quickly begins to reach the astonishing production rates required to explain the observed dimethyl sulfide concentrations. There is also the profound question of evolutionary pressure. On Earth, phytoplankton, as we've noted, produce DMSP primarily to regulate their internal salt balance, an osmotic function. The subsequent production of dimethyl sulfide is, in essence, an accidental, if beneficial, side effect. But what if organisms on this distant world utilize dimethyl sulfide for a different, more intentional purpose, such as communication? Bacteria on Earth are known to use intricate chemical signals to coordinate their behavior, a fascinating process known as quorum sensing. When enough bacteria gather in a specific location, their chemical signals reach threshold concentrations that trigger collective, coordinated responses. Perhaps dimethyl sulfide serves this very function there, with organisms deliberately producing it in immense quantities as a means of intra-species communication. Energy availability is, of course, the fundamental driver of biological productivity on Earth. Photosynthesis, the capture of sunlight, converts solar energy into chemical energy, which then powers the vast majority of our planet's food chains. This distant ocean world, by various estimates, receives similar amounts of starlight energy as Earth. Its red dwarf star, however, emits a greater proportion of its light in the red and infrared portions of the spectrum compared to our Sun's broader, more balanced spectrum. But some Earth organisms, such as purple bacteria and certain cyanobacteria, are remarkably efficient at photosynthesizing using predominantly red light. Life there might have adapted similarly, evolving specialized photosynthetic pigments and pathways to utilize the specific wavelengths of light available from their dim red sun.